Hello for the first time class and welcome to Differential Calculus. In this first mock lecture, we're basically going to be going over what the motivation for studying calculus is in the first place, and I'm going to do that with this thing called the tangent problem. So there's this problem that exists, right, with finding the slope of a tangent line, and to introduce it we need to know two things. First, we need to know what even is a tangent line, and if you think about a circle, any 2 points on the circle that are connected with the line is called a chord. And if you extend that chord in both directions, such that you have a line that's intersecting the circle in 2 points, that's called a secant line. And if you just drag this secant line down until it's coincident with the circle at only 1 point, which is called the point of tangency, then you're looking at a tangent line. Now, in this class, we're not going to talk too much about circles because on the Cartesian coordinate system, those are not even functions. It fails the vertical line test. But instead, we can apply the same idea to a curve. So a curve has many different tangent lines. In fact, it has infinitely many tangent lines. And even though you could theoretically draw a tangent line, like, I don't know, can I find one that's on here? Yeah, you could draw a tangent line here, that looks like it intersects the graph at 2 different points. That is the worst line I've ever drawn in my life. Just pretend that it's it's only coincident with the point at 1. That's a little better. What we're talking about is just like a local, right? Within its vicinity, right? It's only intersecting the curve at 1 point, so it's still technically a tangent line. The second thing we need to know is average rate of change, which is actually maybe something that you've looked at before. Typically it's taught in a pre-calculus class, but I'm just going to do my best to give a really quick rundown on the average rate of change. So if you open any math textbook that has pre-calculus context in it, you're going to probably see a graph that looks very similar to this. What we're going to do is we're going to try to figure out what the average rate of change is on the unspecified interval, or maybe arbitrary is the right word, interval x to x plus h. And we're doing this on purpose, right? We're not calling this x1 and x2 because it's easier to think about the actual horizontal distance between our x values as a single value, which in this case we're calling h. But basically we've got 2 points and we're going to find the slope of the line that connects them. You can find the slope of a line by using the slope formula, which is usually m is equal to y2 minus y1 divided by x2 minus x1. But in this case, x1, y1 is the point x f of x, and x2, y2 is the point x plus h, comma, f of x plus h. And if you stick those two things into the formula, you get this. The denominator simplifies because x minus x is just 0, so you just get h. And that is the average rate of change, right? It's the slope of this secant line, which is basically telling you, hey, here's the average slope of just this part of the graph. And obviously, if you change the interval, so too does your average rate of change, right? Like now we're talking about the average rate of change on this part of the graph, which is much steeper, right, than the last one. So now that we know the two things that are going to help us understand what the problem even is, let's talk about the problem. The average rate of change is telling us what the average rate of change is between 2 points, right? It's fundamentally a secant line that we're finding the slope of. But what if I wanted to find the slope at only one of these points? Maybe this one, right here. That would be the slope of this tangent line. We'd have to use y2 minus y1 over x2 minus x1 on it. But the problem is x1, y1 and x2, y2 are the same point in this case. They're both x comma f of x, right? That's what this point right here is, x f of x. And if you use this as both your first and second point, you're going to get 0 over 0 when you calculate the slope for that thing. And that is undefined. That doesn't even make sense, right? It's actually something that we're going to call later an indeterminate form. We don't actually know what 0 divided by 0 is. It could be a number of different things. But the point is, it's undefined in this context, right? We don't know what that even is. To give this a more concrete example, let's say that we wanted to find the slope at the point 1, 1 on the graph f of x is equal to x squared, right? So we need to know this. Here, the point's 1, 1, and if you try to do the slope formula with this thing, you have 1 minus 1 divided by 1 minus 1, which again, 0 over 0, doesn't make any sense. So what we can do though, right? And so that, by the way, that's the problem. The problem is we can't use the slope formula on 1 point to find an quote unquote average rate of change. So what we can do to fix this problem is we can look at a secant line, right, where we're looking at some point P, which in this case is 1, 1, and then a point Q that we can move around. And specifically what we want to do is we want to move point Q closer and closer to point P, all the while finding some average rates of change and seeing if there exists some kind of pattern. In this particular case, we should see that the slope is converging to some specific number, and whatever that number is, that's what we're going to use as our guess for the instantaneous rate of change. So let's find some slopes where Q gets closer to P. In this first one, right, we're up here. This looks like it's the 0.39, right? The first one is still 1, 1. So that's what we're going to be using. I'm going to set up a nice table here to keep track of all this stuff. X is going to be like our X1. X plus H is going to be like our X2. Oh my gosh, my pen is, I'm losing it. There it is. X2. So that's going to comprise the denominator. But in reality, all I'm going to do is I'm going to look at the rise, right, divided by the run. Right, the run is going to be the horizontal distance that we're looking at. The rise is going to be the vertical distance. So in this first one, right, we have X is 1, and in fact, X is going to be 1 for all these because we're not moving that point. The point Q is the one that's getting closer to point P. In this one, H, the distance between our two X coordinates between 1 and 3 was 2, so that's why I have 2 listed for H. And what I'm going to do is I'm going to make H closer and closer to 0, right, which is going to make these points, right, this point and this point, horizontally almost right on top of each other. X plus H in this case is 3, so 3 minus 1, that's our denominator, that's 2. And then our numerator would be 9 minus 1, which is 8, so we get average rate of change for this thing as 4. Again, I even put it on here, right? X1 is like our X, and X2 is like our X plus H. But now let's start moving P closer, right? Let's move it 1 unit closer in this case. Here, we're looking at the point 2, 4, right? That's what this is, 2, 4. Obviously, this is still 1, 1. Now let's calculate the slope. X is 1, H is 1, because it's 1 unit away from 2, and that makes X plus H 2. 2 minus 1 is 1, so again, this X plus H minus X gives us the denominator, which is 1 in this case, and then 4 minus 1 is 3. That's what our numerator is, so 3 divided by 1. So now we have a slope of 3. So not as steep, which I think you can visually see, right? Here's the first one, pretty steep. Here's the next one, still steep, but not as steep. Okay, let's move it closer. Here, I moved it to the X coordinate 1.5, Y coordinate 2.25. And again, remember, if you're wondering, how the heck did you get this? All I did is I squared 1.5. I'm plugging it into the function to get its corresponding Y value. So here, X is 1, X plus H is 1.5. So that means H is 0.5, which gives our denominator to be 0.5. 2.25 minus 1, because that's what this point is, right? Y2 minus Y1 is 1.25. So now we've got 2.5. So these numbers seem to be decreasing, right? Let's move it even closer, right? And so that's the slope here. All right, now let's move it even closer. So here I'm at the X coordinate 1.25, which means that H, we'll see here, is going to be 0.25. Y2, 1.5625 minus Y1 is going to just be 0.5625, and if we do that division, we get 2.25. And I think I moved it even closer. Yeah, I did 0.1. So the distance, I'm at 1 to 1.1, so our denominator is 0.1, and then 1.21, which is 1.1 squared when I run it into the formula, minus y1, which is, again, always 1, gives us 0.21 as the numerator. 0.21 divided by 0.1 is 2.1. But I moved it even closer, and I found that 2.01, right, was the slope when it was only 0.01 units away. So what does it seem like we're approaching? We started off decreasing pretty quickly, but then, I don't know if you're familiar with the term diminishing returns, but that seems to be kind of what's happening. At each stage we get closer, we're still decreasing, but the amount that we're decreasing by is decreasing, if that makes sense. But I think, right, it's reasonable to assume that the instantaneous rate of change, right, the slope of the tangent line at 1 would be 2. This is called a limiting process, what we're doing here. We're looking at what the slopes seem to be approaching as we made the point Q closer and closer to point P, and P in this case being the 0.11. We could do this from the other side as well, right? I only came from this one side here, but you could do it from the other side. You know, if you started Q here and then started moving it closer, it looks like you're going to get a negative slope. But then as you start making Q closer to P, now here we've got a positive slope, and then we're going to increase the slope until we get up to 2 instead of decreasing the slope because we're coming from a different side. But the moral of the story here is it seems to be that as Q, right, approaches the point P, the slope of this secant line, which is this dotted blue line, is approaching the slope of this pink line, which is the tangent line. So I said M subscript secant, that's the slope of the secant line, M subscript tan, that's the slope of the tangent line. This arrow, by the way, is probably new for you, but it reads approaches, right? So as Q approaches P, the slope of the secant line approaches the slope of the tangent line. Now in this particular example, we can replace the Q approaching P with as X approaches 1, right? Because you're just taking the X value, whatever it is, and we're making it closer and closer to the value 1. Here, in this example, it looks like I'm coming from the left. In the first one, we were coming from the right, but we were limiting X to be what we wanted it to be, right? We were trying to make X approach a specific value. In this case, it's 1. And then I could replace this part with the slope formula, really just this part with the slope formula. X squared minus 1 divided by X minus 1. Now you might be thinking, how the heck did you get that? But remember, this is just generalized slope for the graph X squared. Slope is y2 minus y1 over x2 minus x1. x1, y1 is the point 1, 1. x2, y2 is the point x squared. So I literally just plugged them into the formula to get this thing. And the way that we would write this, right? The way that we can write this information to not have it be a big sentence like this every single time is to use the notion of a limit, right? So this, how you would read this is you would say the limit as x approaches 1 of its slope is equal to 2, right? In this particular example. Right, that's how we would say this. The limit as x approaches 1 of its slope formula, x squared minus 1 divided by x minus 1 is equal. In this case, we're guessing that it's equal to 2. So basically, to kind of put this all into perspective, I think about something like the limit as x approaches 1 to mean that x is getting as close as possible to the number 1 without actually being the number 1. Right? So we can make it as close as we want. What's happening as x gets close to 1? So we can look at a pattern, right? What's going on when x is 1.000000001 or 0.9999999? Looking at those things can give us an indication about what the slope is approaching. And we can generalize this idea of a limit, right? If you have some arbitrary graph, right, with points P and Q, we've got a slope of a secant line. We want to find the slope at P, so we want to find the slope of this tangent line. And again, we have this sentence, right? As Q approaches P, we know that the slope of the secant line is going to be approaching the slope of the tangent line. Well, in a generalized format, right, where we don't know what we're trying to make X approach because we haven't picked a value, essentially you're just making H, right, the distance between your two X values, approach 0. Right? What is happening as x approaches 0? So here we would say the slope of the tangent line, right? The slope of this pink line here is equal to the limit as h approaches 0 of the slope of the secant line. And remember that the slope of the secant line is just given by the difference quotient, right? The average rate of change between 2 points. But we're looking at what happens when those 2 points get closer and closer and closer and closer together, right? That's the idea of a limit. But remember, the slope of the tangent line is the same thing as the instantaneous rate of change at P. That's kind of the takeaway, right? It's an instantaneous rate of change. If I could give an analogy, it would be something like this. Let's say you drive your car to work, right? You map your drive to work, you graph your drive to work where you have your independent variable being time in minutes, your dependent variable being the distance that you've driven. So it makes sense, the longer you drive, the further away you go. You know, when your line's flat, maybe that's like a red light or something like that. So you're not moving at all, and then the light turns green, so you start moving again. We could find the average rate of change for your entire trip by just finding the slope of the secant line that connects where you started, right, time 0, and when you parked your car at work, right? We could do that. That's something we can do with the slope formula. But if you wanted to find an instantaneous rate of change, you'd have to find the slope of some tangent line at time A. Maybe you want to find it here, right, arbitrarily. Maybe this is only like 5 minutes into your drive. But the analogy that I would make is finding the slope of this tangent line, right? This instantaneous rate of change at time A is the same as if you're in the car actually driving, just looking at your speedometer, right? Your speedometer is going to tell you what your velocity is, right? Usually in miles per hour. But here, the slope is the same thing. Although instead of miles per hour, it's actually miles per minute. But finding your instantaneous rate of change is the same thing as looking at your speedometer in your car, right? How fast are you going, right? And speed in this case actually is the slope, because when you take distance like miles and you divide it by a time unit like minutes, you get distance per minute, right? Miles per minute, right? That's a speed. So it's the same thing. So what is an instantaneous rate of change? It's like looking at the speedometer of your car, right, when you're driving. So I hope that helped. The main takeaway here is that limits are important. That's really the whole point, right? If there's one takeaway from all this stuff, it's that we need to study these things called limits. And that's where differential calculus starts, right? To understand what a derivative is, we have to know what a limit is first. And so that's why we're going to be studying it for the next few videos here. So hopefully that was helpful. If you guys have any questions, don't hesitate to send me an email or leave a comment below. Thanks a ton for watching, and I'll see you in the next one.